ring the bell. So first thing I want you to do is this is a warm-up example on the first law from last class. So you're going to need to find the work and use the first law to find thermal energy change. So get to that. It'll probably take about 3-4 minutes. So I'll just tell everyone in advance, I'm not like super sick, but I have the sniffles, so I'm going to sound a little nasal, and my eyes might start watering. I'm not like holding it together up here. I just have the sniffles. So. And to everyone taking the Calc 2 exam tonight, including the many people who are skipping to study on the Echo, which I do respect, actually. My prayers are with you. Sequences in series are pretty brutal. Next stuff you're going to learn, though, Taylor, Maclaurin expansions, those are actually useful, so hang in there. Might be worth saying this problem is exactly on the homework, so you can basically do your homework right now by doing this. All right, so anybody need like a couple more seconds to work on this? Finish the last calc. Worth saying that every example we do today is straight off the homework, including on Friday. Today and Friday, we'll each have one of the maybe I'll call, they might be like some of the hardest examples in the class if you were to go at them alone. So we will, again, every example will be off the homework, so definitely worth your time to work on. All right, so this one, like I said, is mostly a warm-up from last time. So first law relates how much the internal energy bank, the thermal energy stored in an object, changes, goes up or down based on how much mechanical work you do by squeezing it. And then you can also increase the amount of energy in the bank by donating or injecting heat from the outside. Okay, and we had this giant war on minus signs in the last class. So the work, you can always write work as minus P delta V. And if you do your signs correctly, if you're careful with what's V final, what's V initial, you should find that work already has the correct sign. So if we do that, okay, V final is V final is smaller than V initial. So this whole thing is a positive number like we want it to be for a compression. Okay, right, compressions inject energy into the gas, increasing its internal thermal energy. Now for Q, we need to decide whether we are doing plus 300 for Q injected or minus 300 for Q injected. So that big table we had last time, if you inserted heat into the system by putting it on a stove, that was a positive Q. This is the opposite. It's donating 300, so Q in is actually minus 300. Okay. The pressure is 400,000 pascals, right? Kilo means 1,000. V final, it's 200 centimeters cubed. So you're like, oh, I need to convert to meters cubed. And you might accidentally just divide by 100 once. But remember that there's 3 factors of centimeter. Each one demands division by 1,000. So really, this is going to be 200 times 10 to the negative 6th for V final. And similarly, the initial will be 500 E negative 6 meters cubed. Okay, and then plus the negative 300 gives me an answer. If you compute the first term, it's 120. Okay, and therefore delta E thermal is negative 180 joules. Questions on this problem? Again, it's very foundational, but still not easy problem. Okay, just want to reiterate, minus P delta V will already have the correct sign if you're careful. And I just verified that down here by saying VF is less than VI, so work is positive like I need it to be. But for Q, you have to maybe decide using your head if you want to use minus 300 or plus 300, depending on if the heat is injected or stolen. Okay, so today we're going to be talking about a couple mixed topics in the field of calorimetry, which is about heating up and cooling things down. Okay, so 2 things can happen to an object when you raise or lower its thermal energy. Its temperature can go up or down, or it can undergo a phase change, such as freezing or boiling. So 2 things can happen when delta E thermal happens, right, when there's a change in its internal energy. Either the temperature of the object changes, or less commonly, a phase change will occur. And again, examples would be boiling or freezing. Okay, we're going to cover phase changes at the second half of class, and we're going to deal with temperature change responses for the first half. Okay. So you can do experiments that measures, I put 100 joules of heat into water, how much does its temperature go up? Or I think probably the easier way is, how much energy does it take to heat 1 kilogram of water up 1 degree, Celsius or Kelvin? And that is what specific heat is going to talk about. Whoa, why is this so loud now? All right, so specific heat, and I'm going to call it the mass specific heat. Even though most people will just call it specific heat, I'm going to be extra specific. The mass specific heat is the energy required to raise 1 kilogram of that substance by 1 degree Kelvin or Celsius. Or I'll say 1 kilogram of material. By 1 degree Celsius or Kelvin, right? Because the step sizes are the same. For instance, you'll find if you have 1 kilogram of water in its liquid phase, and you inject heat into it, maybe by heating it over a fire, you'll find that no matter what the temperature, to raise it 1 degree, it requires 4,190 joules, which is 420 times 10 to the third, or times 10 to the first. You guys realize how unnecessary that scientific notation was, right? Okay, so you'd say the mass specific heat of water, which I'm going to denote by a little c, is 4190 joules per kilogram Kelvin. Again, this is a material property. It depends on what you're actually heating up. Okay, so obviously, if you're talking about heating up 2 kilograms of water, it requires twice that much heat. Or if you want to heat it up by 2 degrees Celsius, it would require twice that much heat. So we can quantify that in an equation. Delta E thermal, which some people write as Q, I'm going to explain that in a second, is the mass of the material you're heating times little c, I'll just call it little c, not v, times delta T. And I'm going to write or Q here, and I'm going to explain this. It's a little bit of a pain. But I'm going to box this equation in a couple of colors. A quick notational remark, the textbook uses capital M instead of lowercase m. The confusion is capital M sometimes signifies molar mass, so I'm just going to use little m, but just be aware your textbook uses capital M. Capital C versus lowercase c will matter, as we'll see in a second. Okay, so why is it Q or delta E thermal? This is a little bit wishy-washy, so one way you understand it is if you increase the temperature by heating something, obviously its internal energy goes up by that amount, so Q injected and delta E thermal for pure heating processes is the same thing. So that's why people use Q or delta E. So you'll see it written in both ways, but just understand it's the energy required to put into a system to heat it up by an amount delta T. A reminder is that delta T can be done in any unit system. So Celsius or Kelvin, you don't have to jump to Kelvin all the time. So Celsius or Kelvin both work, right? Because delta T, whether you use Kelvin or Celsius, the size of each degree is the same, so the delta T will be the same. Okay, and one more remark is there is an alternate form of this equation which we will use a lot. Here we're talking about heating up each kilogram of substance, but it's also very useful to talk about how much heat is required to heat up 1 mole of a substance. So an alternative form of this equation is, instead of using m, we're going to use n, the number of moles, times capital C times delta T. Okay, and capital C is called the molar specific heat as opposed to the mass specific heat. And instead of kilograms in the denominator, it's joules per mole Kelvin. You probably use this more in chemistry. Or I should say you've had experience with this form more in chemistry. And you've probably done both, actually. Okay, so again, 2 different forms of the same law telling you how much energy change is required or occurs as you heat a substance. Anybody need more time to copy stuff down? All right. So we're going to do a quick example, and then we're going to do one of the bigger examples after I'm going to walk you through it. So here I tell you the molar specific heat of a gas, and I actually use the last question, which the answer was the internal thermal energy decreased by 180 joules. And I ask you to find the actual temperature change that would have occurred on that gas in the previous problem. This should be pretty quick, so I'll give you 3 to 4 minutes to do this one. And also, just keep in mind your minus signs. See if you expect the temperature decrease or increase, and make sure the minus signs tell you the appropriate sign. Anybody need more time on this one? All right, so pretty straightforward one using the equation we just learned. So I tell you the molar specific heat of the gas, so you want to use the molar form of the equation. Okay, I tell you delta E thermal is negative 180. You have 2 moles of gas. C is almost coincidentally exactly 3/2 times the gas constant, which seems a little strange, but we'll actually see that's universal for all monoatomic gases in existence, which is extremely, extremely strange. But you actually will learn why if you take an advanced thermo course, or I might even tell you. Okay, and then all you have to do is divide the 2 times 3/2 R over to the other side, and you'll get delta T equals negative 7.2 degrees Celsius or Kelvin. Okay, so it's a temperature decrease as it lost thermal energy, which is exactly what you expected. Okay, so now we come to one of the best examples in the course. Okay, this is a calorimetry problem. And it includes probably one of the best lessons in math that I've ever learned. So the question is, you have, and I'm going to do this one, this is not your example. And this one comes directly off the homework as well. This is one I would consider a tough problem. So I have a bucket full of water at 20 Celsius, and I drop some extremely hot metal into it. Okay, so drop copper, and it's been heated to 330 Celsius, and I drop it into a certain amount of water. And the question is, find the temperature of the whole system once the copper and water have reached the same temperature. Okay, now immediately there's a problem. The copper and the water start at different temperatures. I don't just tell you the water absorbs 180 joules, or the copper cools to a certain temperature, find the new temperature of the water. What I ask you is they both approach the same final temperature. So the water is going to heat up and the copper is going to cool down, and they're going to settle at the same temperature. Okay, so we end up in this sort of circular situation where we don't know how much the pellets will cool down, so we don't know how much the water will heat up because we don't know how much heat the copper transferred into the water. Does everyone see the problem there? Like, we don't know how far down the copper's temperature is going to go, so we don't know what temperature the water will rise to. So it seems like we're stuck. Okay, now, it turns out you're actually not stuck, and it turns out this is actually a signal that you should do something. Okay, and I didn't learn this until I was a senior, which is kind of mind-boggling that you can be doing field theory research and not understand this. But I just don't think anyone ever explained it to me, so I never realized it was a thing. So whenever you run into this circular situation of you don't know how far one thing goes down, so you don't know how much the other thing goes up, and it seems like you can't find it, it's going to be a signal to do something specific, and I'll show you where that occurs in the problem. Okay, so the general idea in these problems is that the heat that goes out of one object is going to go into the other object, right? The copper gives off heat, and all of that heat is absorbed into the water. Okay, so I'm going to write this as like sum of Q equals 0. And I don't have its own slide for this equation. I'm just going to put parentheses next to it, calorimetry problems. Okay, this is like the main concept. Basically, all the heat that goes out gets absorbed by one of the other objects in the system. Okay, so as I will talk about more in the phase change version of this problem, the amount of heat given off by the copper is going to be m copper times C of the copper times delta T of the copper. Okay, this is the heat given off by copper. Okay, and I'm going to just ignore signs for now. We'll see that all plus signs is the correct convention. Plus the heat absorbed by the water okay, so the heat given off by the copper, delta T for the copper is negative, so this will be negative. Oops. Heat absorbed by water. I'll let everyone copy that down, and I'll explain how you get out of the sticky situation. Some of you might already see how you can get out of it. It's something that some people just get. I did not get it. Okay, so again, the issue is we don't know delta T copper, but we also don't know delta T water because we don't know what temperature the copper ends up at, so we can't use that to find delta T water. Okay, the signal, it's a signal to, I'll put it in quotes, it's a signal to use variables, and the signal is that the same variable will appear in two places. Now, when you have the same variable appearing in different places in an equation, it doesn't really matter. It doesn't make the equation any more or less solvable because you still have one equation and one unknown. It's just that the same variable will appear in two places. Okay, so the signal is write this in terms of variables with T final being some unknown number. You don't know it on either side of the equation, but it's still only one variable and one equation. So if I write this out, so T final copper minus T initial copper, mass of water, specific heat of water, final temperature of the water minus initial temperature of the water. Okay, and the copper and the water reach the same temperature, so I'm just going to call it T final instead of T final water and T final copper. Okay, and now tell me, how many equations, how many unknowns do you have? One equation, and even though the unknown appeared in two places, it's still only one unknown in the equation. It's easy to solve. You'll combine the 50T with the 80T to get a 130T. The equation is just as easy to solve. Okay, so this is why writing equations in terms of variables when you think you're stuck, this is why it's so valuable. It's easy to get stuck in the circular way if you do not write down this equation, but when you get stuck in the circle, it's a signal to just write the equation with the variable, and the same variable is going to appear in two places. So you're actually never stuck to begin with. You just need to write the equation out with the variable in both places. Okay, again, this is a very important lesson that when you feel stuck in a circle in an equation, you should probably write it with the variable in there, and it'll just be one variable in two places. Okay? I stress that a lot, even though it's a simple concept, because it's extraordinarily important, and it was not simple for me to figure out. I figured this out after I nearly bombed a general relativity test, because I did not know how this worked. Okay, if you at this point you know everything in the equation. You know the mass of water, specific heat of water, initial temperature of the water, and copper, and all the other numbers. So if you plug in every number here, you'll get a final temperature for the copper and water of 30.4 degrees Celsius. Okay, everybody understand my point in that example? You're going to use this a lot. Maybe not too much in this class. For calorimetry, you obviously will. You're going to get a lot of these questions, but in general math and your life, this will be important. Because people who don't understand it, problems are literally impossible to them that will be easy to you. Okay, so first half of class, or a little bit more than half, was about temperature changes in response to heat injections, or changes in thermal energy. Now we're going to talk about how phase changes eat up thermal energy. Equation-wise, it's very simple. Minus sign-wise, not so much. Okay, so a phase change is when you add in heat or change a substance's thermal energy, but the temperature doesn't change. So add heat / thermal energy. Obviously, you can take it out and do the phase change in reverse, like freezing. But so you add heat or thermal energy, and delta T doesn't go up. Instead, freezing or boiling happens, or condensation, blah, blah, blah. Again, you can sort of understand this as melting the bonds between the atoms instead of giving them actually more kinetic energy. You're destroying the potential energy of binding. Again, it's kind of weird when you heat up an ice cube. The ice cube doesn't heat past 0. It stays exactly at 0 until all the ice is gone, and only then does the water start heating up. And for temperature increase, we had this idea of how much energy do you need to inject to heat up 1 kilogram of water by 1 degree Kelvin. Here, there's a similar thing called the latent heat. That's how much energy it requires to freeze or boil or whatever 1 kilogram of substance. So latent heat. And actually, I'm going to call it 2 separate latent heats. There's a latent heat for the liquid-gas transition called the latent heat of vaporization. And then there's also the latent heat of fusion, which is for the solid-gas transition, so freezing or melting. I suppose there's a third one for the deposition sublimation phase change, but it doesn't have a name because it isn't used too often. So latent heats of vaporization and fusion is energy required to, in the case of vaporization, it's boil or condense. And in fusion, it's freeze or melt. 1 kilogram of substance. Okay, and it's just sort of a fact that if you need to put 200 joules in to boil a kilogram of something, condensing it will release 200 joules, so there isn't like a separate size number for freezing versus melting. It's the same size, but it's just the energy goes in one case and out in the other case. The latent heat is defined as the positive number. So it's like the energy required to or energy required inputted or released, depending on the direction of the process. Okay. Okay, I'm just going to say this before we get to an example. In an equation, so you guys remember how MC delta T and negative P delta V, they already had the correct minus sign in front of them, and we were just like double checking that it was what we expected. And for Q, on the flip side, we had to manually insert the minus sign based on if it was an energy injection or subtraction. Same thing for phase changes. We're going to have to use our noggins to decide whether you want to have a plus sign or a minus sign, and this trips people up. So in an equation, you must insert minus signs by hand. There's no other option. There's no, no amount of calculus can save you from needing to put these minus signs in, even if you're perfect with all your minus signs. This is not optional like it was in some cases. Okay, and I guess I'll write this on this slide. So, okay, I'll write this here for reference, and I'll explain what I mean on the next slide. So, a positive sign, or okay, melting or boiling, so going to the higher energy state. I'm going to say it comes with a plus sign. And again, I'm going to have to explain what I mean by that on the next slide. And freezing or condensing comes with a minus sign. And again, I put these in quotes. And I'll say for calorimetry problems, okay, only. Otherwise, use your head. Otherwise, you gotta think. And there is simply no way around it, unfortunately. Like I said, for voltage and stuff, if you were careful with your integration bounds, you could get around the minus signs. You're going to just have to think for this one. There was simply no shortcut. Oh, and I should actually write the equation. It's that the delta E thermal, or heat, it's equal to the constant, which is called L, times the mass of the substance. Again, you sort of knew this. L was the amount of thermal energy required per mass, so I just multiplied M to the other side. Okay, and some people will write L with an F subscript for fusion and V for vaporization. Obviously, depending on if you're boiling or melting, you use the appropriate L. Okay, so vaporization is called LV, and fusion is called LF. And again, this is in contrast to MC delta T. That was how much delta T will occur if you insert a certain amount of delta E. Here it's how much mass will undergo a transition. It's mass that undergoes the transition. It's not the total mass of the object. If you melt the whole object, then it is. But this tells you how much mass will be converted by a certain amount of energy. Mass that is converted. Everyone understand the difference? If you don't put enough energy in, the whole object doesn't melt. Only little m melts. Don't need more time copying stuff down this slide? Okay. Oh, okay. Actually, so what I was thinking about writing should have gone on this slide. So this is a blank slide. Okay. So this is a very similar problem to last time, where I have, okay, well, I suppose I'm putting a cold object into a hot bath, but this time, the thing that I put in is going to change phase in addition to changing temperature. So I put in an ice cube, and instead of it being water at 0 Celsius and it just heats up, first the ice melts, becomes water, then the water and the hot reservoir of coffee will equilibrate temperature. Okay? Now, again, the principle is you add up all the Q's, and it should give you 0. But this time, you also have to put in either plus or minus L times M, assuming that the whole object melts. Okay? So what I want you guys to do is write out the entire equation with all the contributions of Q. Now, MC delta T already comes with the correct sign automatically, so it's always plus. decide whether you need to use plus L or minus L, and get the equation down to the form where you could plug in numbers. It's one variable, one unknown. Okay, this appears on the homework, and it is a very hard problem if you are not careful with it. If you are careful, it's an easy problem. Okay, actually, I should explain something really quick. Sorry, I forgot to explain it. So on the last slide, I said that when things melt, it's a positive number. I want to explain why that is. So in this case, once the ice cube melts, there's going to be M water, C water, delta T water. Okay? This is going to be a positive number because the water is heating up. It requires an energy injection to heat up the water, and it comes with a plus sign. So for consistency, everything that requires an energy injection or stealing from the heating object is going to come with a plus sign. So that's why for melting or boiling, it comes with a plus sign as well. Okay? All right, now you can go ahead and write the equation. I'm going to write down all the heats involved. Easy to go in circles on this one if you don't write this equation down. I'm going to, just because we have about 1 minute left, I'm going to start explaining it. So really, you're just writing out in a table, I did it, all the sources of heat in or out with the appropriate signs. So MC delta T's automatically have the correct sign. You never need to mess with them. Only thing you need to choose is if it's plus LFM or minus LFM. And for melting, it's a plus sign. So all I'm going to do is add up all the sources of heat emission or absorption, which is just adding up the right side of the table, and then equals 0. And at that point, you know every variable. It's directly told to you once you substitute delta T as T final minus T initial. Okay, so LFM plus sorry, M ice, M water, C water, T final water minus T initial water, plus M coffee, C coffee, T final coffee minus T initial coffee equals 0. Right? All I did was replace delta T for each object with T final minus T initial, and then the two T finals are the same when they're in equilibrium. Okay, and if you count, you know every number in this equation except for T final. Just one remark is T initial for the water is 0. As soon as it comes out of the ice, it's ready at 0 because it was just ice. All right. Feel free to ask me questions. Good luck on calc tonight, guys.